Yeah, it's easier than me saving to the hard drive and then uploading later.
Yeah, that's
Okay. Uh, so this mask looks funnier, but it gets less foggy. Okay. So we already talked about this, but we are going to be talking about intermolecular forces because they're everywhere in biological systems. Yeah, so how the protein folds, how DNA is put together. It's how we taste things, it's how we smell things. It's all intermolecular forces. So something that smells like mint, it's because a molecule fits inside this receptor in your nose or your tongue. And it's not binding, it's not bonding to it. It's just fits this this shape and it will do intermolecular. You will use intermolecular forces to cause your nerves to say, "Hey, there's something there. It must taste like this." I mean, that's as much as I can tell you about taste. It's pretty complicated, but it's all intermolecular forces. So we're gonna get into that in a second. But in order to talk about intermolecular forces, we need to have a better framework for understanding the different kinds of molecules we're going to look at. And we're going to be looking at organic molecules. And organic molecules, organic compounds, these are molecules that have to contain carbon and hydrogen, generally carbon and hydrogen bonds. They can also include other things, but I think the bare minimum is it has to have carbon and hydrogen in it, okay? And not just a carbon and a hydrogen, but a carbon-hydrogen bond somewhere, okay? So ethyl alcohol, this is the most common organic, well, that's not the most common. It's a very famous molecule. There's a bunch of carbon-hydrogen bonds in it, so this is the condensed structural formula. You got to get used to seeing this. It's got many different names. Ethyl alcohol, it's not even the systematic name. It's actually called ethanol. A little bit different, but it's also called grain alcohol. It's got a lot of names. There it is. Even soaps, which are made from fats, fatty acids, these are organic. They're long chains of carbon and hydrogens. So here's a line drawing. Got to get comfortable with seeing the line drawings as well. Just to remind you, each endpoint and each bend is a carbon, and we know that carbons should have 4 bonds total. So if there's only one shown, so this carbon here is bonded to one other carbon, the other 3 bonds must be hydrogens. Hydrogens are implied in line drawings. And if it's not a hydrogen, you've got to explicitly write out, or a carbon, you have to explicitly write out the atom. So oxygen, oxygen, sodium, for instance. But anyway, that's a very, that's an organic compound, lots of carbon-hydrogen bonds. Dyes and drugs. Here's a famous drug, caffeine. And this is a ball and stick model. So the color coding isn't necessarily the same in every case, but usually blue is nitrogen, usually red is oxygen. The gray, black colors are definitely almost always carbons. And white is very commonly hydrogen. You can kind of see from the size that the hydrogens are much smaller than the rest of them. But anyway, that's organic too. You've got a lot of carbon-hydrogen bonds in there. So first things first is just understanding, are you looking at an organic compound or an inorganic compound? And I'm going to leave this on the whole time, so I'll just show you people vote. So yes, 100%, it is definitely organic. It will start. Come on. There we go. There we go, organic. What about this one? You can just change your vote if you need to. So this one, pretty clearly inorganic. So I didn't change your vote. I'll just clear it out. There we go. Stop. Start again. So the next one, this one, that one's kind of easy to see. Definitely organic. Good. Come on. There we go. Need to wait like a half second for everything. This one. All right. I don't think these are very hard. All right. That one is definitely inorganic. There's no carbon-hydrogen bonds. This is one that always gets people. If I draw this out, does that look organic or inorganic to you? It is inorganic. So people often think, oh, it's got all these covalent bonds, double bonds, it must be organic. No, this is inorganic still. As long as it needs the hydrogen, it needs carbon hydrogen. This is definitely inorganic. So CO2 is inorganic. It'll be pretty clear. Organic, you have to have those carbon chains and hydrogens and stuff like that. Okay. We're going to be kind of bouncing around. Well, we're not going to bounce around too much. But when you are reading about this, you're going to be bouncing around in the textbooks. So just, you can come back to this slide if you need to. Kind of the general purpose, what organic compounds are, is in section 4 in the Mastering Chemistry book. We're going to focus on categorizations of organic compounds, so like the kinds of compounds you could make. And here's the names, we're going to get to them. So functional groups, and we'll get to those as well. We'll talk about that when we get to it. That's kind of stuff will be on a quiz or an exam. So let's start with these hydrocarbon types. So first of all, hydrocarbon is a specific kind of organic compound. And it's really referring to the fact that it's mostly a carbon-hydrogen compound, okay? It's a very generic term. So what kind of hydrocarbons can we make? Well, there's alkanes, alkenes, alkynes, and aromatic compounds. And the distinction is fairly simple. If it's all single carbon-carbon bonds, then it is an alkane. So it doesn't matter how many carbons there are in the chain, as long as it's all single bonds to the carbons, it is an alkane. Alkanes always end in the A-N-E ending, so this ethane is an alkane because it's got the A-N-E ending in it. We'll come back to the first part in a second, but let's keep going. An alkene, as long as it has one double bond in it. One double bond, it is automatically an alkene. If it's got two, it's an alkene still. But minimum one, it's an alkene. And an alkyne is a minimum one triple bond. And if you want to ask me, well, what if you have a triple bond and a double bond? It gets complicated, but it is technically an alkyne. So we're not going to talk about that. Just notice that we're really focused on the fact that there's a triple bond in there that's an alkyne, okay? The last one's a little tricky until you get comfortable with seeing it, but benzene is what you're seeing here. And we've talked about benzene before. It's got alternating, if you draw the Lewis structure, it's got alternating double and single bonds. And so that should immediately scream at you, hey, resonance. This does resonance. Basically, we can draw the exact same thing, and I'm not going to draw it because that's too much trouble. But you can draw the same structure where the double bond is here now, and this double bond is here now, and this double bond is here. Everything's shifted over by one. And remember why we do resonance. So resonance is a flaw in Lewis structures. If I were to go and actually somehow measure the bond length of each carbon-carbon bond here, so single bonds are longer, double bonds are shorter. So if I go and measure the actual bond lengths in this benzene ring, I would not get long, short, long, short, long, short. I would get them all the same length, all of them. And that is because the true picture of this is that these double bonds are constantly moving around. And there really is, these electrons are delocalized. There actually is 1.5 bonds between every carbon. And when you have that kind of scenario where there's resonance, where the double bond electrons are delocalized, this is generically called an aromatic compound. So you'll see this, you'll see a benzene ring. somewhere in there. We call it phenyl ring in organic, but there might be more carbons attached somewhere else, but that ring system there makes it aromatic. It has nothing to do with smell, although it might be related incidentally, but it's just called an aromatic. So, another term, which you have heard before, I know, is the word saturated. Alkanes are considered to be saturated. And what that means is there's only single carbon single bonds in it. The saturated part refers to the number of hydrogens it could potentially have. And saturated means it's got the max number of hydrogens. If it's unsaturated, whoops, there we go, then there is a double or triple bond or it's aromatic. And the idea is, well, I could add 2 more hydrogens here and turn it back into a single bond. So it's unsaturated in terms of the number of hydrogens it can hold.
So all 3 on the bottom are unsaturated?
Yes. And if these terms sound familiar, saturated fats, unsaturated fats, it's exactly the same thing. A saturated fat is a fat, usually a long carbon chain with acid sitting on the end that makes it a fatty acid. But the saturated fat has no double bonds in that chain, whereas an unsaturated fat has at least 1 or more double bonds in that chain. I believe the research is now leaning towards saturated fats are fine for you. Used to be they were bad for you, and the reasoning was when you have an unsaturated fat, a double bond somewhere, it's easier to break the fat down at the double bond. Like it's easier to break it there, even though that's a stronger bond. And we'll get into more, well, we'll talk about that another reason. But anyway, we don't, like the current research now, I believe, is that saturated fats aren't that bad for you anymore. Because like what coconut oil is like, I think it's a saturated fat. And people like gobble that down, so I don't know. I'm sure the research shows that it's not so bad anymore. Anyway, I don't know specifically. But anyway, that's what those terms mean. Okay. So let's talk about the carbon chain length. So when you have 1 carbon, methane, carbon with 4 hydrogens, up to 5 carbons in a chain. So ethane, which was on this previous slide. Next is propane. Everybody's heard propane, right? Propane gas. After that is butane. That's what goes in the lighters. Pentane, nobody works with that, but we do that in the lab. Most of those short chain carbons have boiling points in the range of below room temperature. So they're gases already. All right, they've already been boiled. The temperature's high enough that they're a gas. As soon as you get to 5 carbons to 12 carbons long, in terms of how many carbons in your chain, the boiling point goes up, and it's a liquid now. This is what gasoline is. Octane, that's the stuff that, if you have a high-performance car, turbocharger or something like that, high compression ratio, you need octane so that it doesn't blow up from pressure. Anyway, that's what those are. When you get to longer chains, more carbons, that's diesel, kerosene. It's still a liquid, but it's starting to get thicker. And then you keep going up, 16 and up carbons. That's where you get to the lubricant area. Like these are with oils that go in your engine that lubricate the bearings and all that stuff. And they're starting to get really thick. Paraffins, this is like the wax, candle wax stuff you, I think people do paraffin dips in their hands and stuff and feet. I don't know. It's a solid, but it melts at low temperatures. But notice the boiling point's going up again. And then when you get to really high numbers of carbons, 36 and up, that's asphalt, the black tar stuff they put on streets. It's a solid. On a really, really, really hot day, it'll get soft. It'll melt, but it's still a solid. So something about the length, the number of carbons, makes the boiling point go up. So we're getting to a clue into how to interpret what that means, but we'll understand that later. Here's another kind of slide that kind of shows what we saw before, but this is specifically 1 through 10 carbons. And what I'll kind of first bring up here is the naming scheme. So last term, 221, you guys learned how to name inorganic binary covalent compounds, right? So something like that is dinitrogen tetraoxide. These prefixes, first elements, keep the same name, second element, IDE ending. For organic compounds, the naming scheme is completely different. It is different, completely different. We're not going to worry about that too much. Maybe the endings and stuff like that. You'll learn this but really well in organic chemistry if you take it. But just so you understand, the first part of the name has a reference to the number of carbons in the main chain. Meth means 1, F is 2, prop is 3, but is 4. And then after that, it starts making a little more sense. Pent, hex, eptok, non, dec. And the ANE ending, that's the alkane. ENE ending would be alkenes, YNE ending, alkyne. So the ending is going to be more important for us. And the ending is going to tell us what kind of organic compound it is. Okay? So ANE ending, these are just straight chains, single bonds all the way. Well, not necessarily straight chains. We'll get to that. The other thing, get used to seeing different forms. So there is the structural formula on the left. We've got the condensed structural formula, this one or this one, same thing. In the middle, we've got a line drawing, and we've got ball and stick. You don't have to draw this yourself, but you can see it at least and interpret it. They're all the same. They're all representing the same thing. In general, the formula for an alkane is predictable based on the number of carbons you have. You can memorize this if you like. So if I have 3 carbons, 3 here, then 2 times 3 is 6, plus 2 is 8. There's going to be 8 hydrogens. You can memorize that, or you can just jot down quickly, 3 carbons. Every carbon needs 4 bonds, so there's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. I draw the hydrogens too if you need to, but it's always going to be 2 for each carbon plus the endpoints have an extra 1. That's where the plus 2 comes from. So, I'm sure I remember what the arrow is for. It might be in the wrong place, because these are all butane, not pentane. So the arrow's in the wrong place. Okay. So, quickly, as soon as I get started, what is the correct formula for something that is 8 carbons long? This is definitely octane, yes. Okay. So, yes, everybody's good. B. It's not too hard. Okay, we're on the right step. We're on the right track. We'll be okay. So let's do hexane real quick. Condensed structural line formula for hexane. So hexane, I mean, probably the easiest thing would be to draw it out. Hex means 6. There's 6 carbons long. 4, 5, 6. 1, 2, 3, yeah, 6. And then carbons, or hydrogens everywhere. So I need 3 extra bonds here. So I have a total of 4 bonds. Here I need 2 more. 2 more. 2 more, 2 more, and then 3 here. There we go. Yes?
That's the condensed or the structural?
Did I? That's the structural formula. Yeah, not condensed. That's the structural formula. The condensed version, you can just write it out in a single line like this, CH3. And then that's a CH2. And then that's a CH2, 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 CH3. Sometimes you'll see things written backwards since this is on the end. Sometimes you see people write H3C. That happens sometimes. Another way to do it is even more condensed. You can do this. CH3, parentheses, CH2, and there's 4 of them, and then CH3. There's many ways to do a condensed structural form. Okay? Condensed just means not the full structure, that's all. But you need to show a little bit of the structure because we're going to see some variations called isomers that will be very different. And then finally, the line drawing. 1, 2, 3, 4, 5, 6. That's it. 1, 2, 3, 4, 5, 6 carbons long. Their hydrogens are all implied. Okay. There we go. And we weren't asked to draw this, but there's the ball and stick model. Notice the ball and stick model shows the geometries correctly. Everything's tetrahedral around the carbon, which is kind of why some organic, we like the easy line drawings. They're very easy to write, but they're actually better in terms of shape. They show off the fact that, hey, these carbons actually do zigzag like this naturally. Okay. Structure formula just shows what's connected. That's it. Doesn't show any shape to it, which is fine. Sometimes it's fine. So now, why are we drawing carbons all in a row? What about some branches? Can we put carbons going off in different directions? And yeah, you can. These are called structural isomers. So a structural isomer is a compound that has the same formula. So this is all C4H10, but they're connected in different ways. So this here is C4H10, that is C4H10. And it's even in the condensed form. So 1, 2, 3, 4 carbons, 3, 6, 9, 10 hydrogens. Same as the one on top. There's the line drawing for this thing. There's the line drawing for the straight chain one. These are very different molecules. One of them is called butane. The name for the second one is isobutane, but it is isobutane, but probably a better name would be 2-methylpropane. And the reason I say that is we often will look at the longest chain, 1, 2, 3. That's 3 is 3 carbons, so propane. And there's a meth group, a 1-carbon group hanging off of it. So, yeah, meth. It's the same word. Methamphetamines there's some kind of carbon group hanging off of a bigger molecule. That's where the meth comes from. They shorten. And the name is meth, but that's just a part of it. Anyway, so there's lots of different ways to name organic compounds. Again, I'm not gonna quiz you on specific names. What I will quiz you on is the generic type. So, hey, what kind of compound is this? These are both alkanes. And then just knowing that these are isomers. These are the same formula, but different compounds. They're just built differently. The last thing right here, we haven't talked about this much, but a space filling model shows the shape of the compound really well. It shows the space it takes up. They're just hard to see in terms of how many atoms there are. It's really hard to tell that there's a carbon in there. But what you can see is that this one is more ball-shaped and this one's more cylinder-shaped. And that's going to be important later on. We'll talk about that later on, okay? So let's try isomers for hexane. So I'm going to do line drawings because they're easy to draw. And let's just do like that. Let's just take a carbon off the end and put it in the middle somewhere. So I'll make a 5-carbon chain. There's 1, 2, 3, 4, 5. And instead of putting the 6th carbon at the end, right there, that is also C6H14. They're both C6H14. But these are isomers. Why put it on this carbon? What about this one? Sure. That's different. So there's 1, 2, 3, 4, 5, 6 carbons still. As long as you don't put any double bonds in it, it's going to have 14 hydrogens. What if I put this on this carbon? Try that a little better, sorry. Is that a different molecule? Now, it's actually these two, even though they look like mirror images. Remember, these are 3D molecules. I could take the model of this thing and then just kind of rotate it, and it will look exactly like this one. So these are not isomers. This is not a new isomer. This is the same as this one. Why move one carbon? We could move 2 carbons. Let's make 1, 2, 3, 4 carbons in a chain. And I'll put another carbon here and another carbon there. That's an isomer, C6H14. Why put them on different carbons? Let's put them on the same carbon. There we go. So there's tons of isomers. The more carbons you have, the more variety you can come up with. Somebody would think, well, what about a ring? Why not a chain? What about a ring? So 6 carbons in a ring. Is that an isomer? How many hydrogens does that have?
We'll have less hydrogens.
Yeah, it'll have fewer hydrogens, yeah. That actually has only 12 hydrogens in it. So that's not an isomer. You can make rings, definitely. They exist, but that's not an isomer. And be careful, and I'm not going to quiz you on this either, but you will get it in organic chemistry. And this is why people hate it, or not hate it, or just throws them for a loop when they take it. So what about this? If I do 4 carbons long, and then I do like that. Is that different? Or does that match something else?
I'm used to that matches something.
So here's the thing. We're not going to do this in this class. I'm not going to catch you on this in a quiz. Don't worry. But in organic chemistry, you're trained to find the longest chain. And here it is: 1, 2, 3, 4, 5 carbons. And this branch is on the 3rd carbon. That is exactly the same as this one, which is 1, 2, 3, 4, 5 carbons long, and the branch is on the 3rd carbon. So these are the same. This is why organic chemistry is hard for some people, because you have to think 3-dimensionally. You have to be like, oh, rotate that in space, think about how that might twist around. You need bottle kits. So if you take organic chemistry, buy a bottle kit. Don't cheap out. Sometimes they make you, so don't worry. Anyway, isomers. There are other kinds of isomers, but the bottom line is isomers always have the same formula. This is a structural isomer. We'll see other kinds of isomers. There are isomers. Actually, we did go across those. We did the S and the R carvone. Was that in 221? Yeah. See, I made you guys smell these 2 compounds, spearmint and caraway seed. They were exactly the same molecule. Everything was connected exactly the same way. The only difference was their mirror images were, they were mirror images of each other, but they weren't you couldn't put one on top of the other. That's another kind of isomer. So anyway, you'll get to that. That's organic. So I mentioned this in the naming scheme. One way to do naming is to name the main chain, and then you look at the branches. What's connected to the main chain? And so if there's 1 carbon connected to it, that's meth. But we put a YL on it to indicate it's a branch, methyl. Ethyl means 2 carbons on the branch, propyl, butyl. And then there's always funnier groups. So this is 3 carbons, but instead of being a chain, it's connected in the middle part. So it's called an isopropyl group. You guys have heard of isopropyl alcohol? So isopropyl alcohol is this with the thing that makes it an alcohol, an OH on it. Anyway, it's a lot of variety. That's why organic chemistry is a little bit tricky for people. Here's tert butyl. That's a butane, but instead of a chain, it's kind of all blocky like that. Again, I am not going to quiz you on what's exactly this name. I will do very, very light touch to this, okay? So this is just so you can see something and kind of understand what you're looking at and not be like, I don't know why it's named like this. So you'll see the name, you'll see the compound, you'll be like, oh, that's what this is referring to, okay? So this is 2-methylpropane, which is isobutane also. That was on the previous slide, but 2-methylpropane. So the naming scheme means propane is the main chain, and a methyl group right here is on the second carbon of that main chain. That's where the 2 comes from. They get crazy. They get really crazy. You get like 2,2-dichloro, 3-methyl, something, octadiene. You know, you get some really crazy names. And that's, again, organic. You'll do that in organic. First term. Okay, so let's get to the functional groups now. We've already covered a few of them, the double bonds and the triple bonds in a regular hydrocarbon, and aromatics. What about if it's not just carbon? So let's include oxygen and nitrogen. And of course, there's other elements too, but we're going to focus on oxygen and nitrogen mostly. If you have an OH attached anywhere on that molecule, it is now an alcohol. If anybody's ever seen sugar, what the sucrose looks like, I can't draw it because it's kind of complicated, but it's 2 rings connected to each other, and it's mostly carbon, maybe an oxygen in the ring. But in addition to that, there's a bunch of OHs attached to it on all the rings. So if you've ever heard of a sugar alcohol, that's, what do you call it? Redundant. Sugars are alcohols, so because they have all these OHs on them. So they are technically alcohols. Anything that has this OH group on it is an alcohol. Not all alcohols are bad. Most of them are very poisonous, but some of them are sweet. Yeah.
So, ethyl alcohol
Uh-huh.
uses fermented sugar.
Yes.
So you're basically making ethyl alcohol from other alcohol, sugar alcohol.
Well, so that's, yeah, it's a little bit more complicated than that. So there's a couple steps in the fermentation process. So I think the bacteria or the yeast will break down the sugar into more simpler compounds.
Yeah.
And then I believe it stops at an alcohol, like at a simple alcohol. But you can keep going, and you can turn an alcohol into other things. You can turn it into carboxylic acid. So this right here, we'll skip the others, we'll come back to it. This is acetic acid. This is vinegar. This is, I mean, if you let alcohol ferment long enough, you'll get vinegar. So the bacteria will oxidize your alcohol into this, and all they have to do is take that carbon and turn it into the C double bond O thing, which is a long, convoluted process. I'm not saying it's simple, but that is a carboxylic acid. So this is what organic acids have on them. Amino acids, the building blocks of proteins, have this on one end. What about the amino part? Well, that's this. An amine is anything that has this NH2 group on it. They're stinky usually, but amines. So an amino acid has this on one side and this on the other side. And when amino acids bond together to make long chains in a protein, they make amides. So this will react with this and make this. And it'll just make a long chain of that. Anyway, so I just want you to notice that it just takes a little bit to make something a functional group. So why are these functional groups, why do we care about them? Well, they drastically change the properties of your compounds, okay? Ethane, just C2H6, is a gas at room temperature. As soon as you change one of those hydrogens into an OH, it's now a liquid, and it's flammable. It still is flammable. It was flammable before, but it's a different kind of flammable now. And then if you change one of those carbons to be a C double bond O, now it's acidic. Small changes to these functional groups will make drastic changes to the properties of your compounds. Esters are fun. A very common lab that you'll do in organic chemistry is make an ester called isoamyl acetate. And when you make that, you'll be like, I know exactly what it is. This is banana ruts flavor scent. So that really artificial banana smell, which is actually the original banana before they got all wiped out by fungus. But yeah, esters are very popular in food chemistry. Another place you'll find amides is if you like searing meat. So when you brown things, you're making a lot of these things, amides.
And that's carcinogenic.
Can be. Some of the compounds that you get from cooking can be carcinogenic. But I think, so the tricky thing with cooking is that it's like a black box. You're making a ton of random stuff. Some of it can be carcinogenic. But what I like to remind people is the dose is what matters. So sometimes the small amounts don't matter at all. But that's hard to say. It's hard to quantify without experimentation.
Steak is one of them.
I mean, it's not just meats. I think
It's also the
onions and
vegetables.
stuff.
So
Yeah.
if you char it, then all of a sudden it can cause more. of a
Well, that's
problem.
true. Yeah, too much carbonation, like too much burning. Yeah, that's bad. All right. So anyway, these are what we call functional groups. Yes, you can have more than one functional group on a molecule. We're going to keep things simple just to make, you'll see why we need to learn these in a little bit. But the ones you're going to be responsible for are not these, even though these are squared for some reason. So here's some other ones. Here's an ether. An ether is an O with 2 carbon chains on either side. The original anesthetic before we got better stuff. Even if you put, so an X here, there's no X element. What they're talking about is a halogen. Anything from group 7 suddenly makes it a haloalkane. So chloromethane, chloroethane, bromoethane, something like that. Here, let me get to the better slide. Well, that's not the better slide, but this is just more. Here's some 2 new ones, an aldehyde and a ketone. So this C double bond O thing shows up in a lot of these functional groups. The C double bond O itself is not the functional group. You have to consider what's next to it. So if there is a hydrogen directly attached to the C double bond O, then it is considered an aldehyde. The most famous one is formaldehyde. Not that one. Formaldehyde has only 1 carbon in it. That's ethanol or acetaldehyde. Do you guys know where the word formaldehyde comes from, the form part? Anybody speak French or Spanish? Know what the word for ant is? I don't know Spanish, honestly, but
And like
the little insect.
okay.
In French it's fourmi. I'm sure in Latin it's something similar, but the origin of formaldehyde is, well, you can make formaldehyde from formic acid, and they would get formic acid by distilling corpses. So they have a lot of formic acid inside them, and that's where the word form from formic acid, fourmi, comes from ants. Anyway, this is old stuff. I like that story. So that's an aldehyde. If you replace the hydrogen and you've got carbons on both sides, that is a ketone. Probably the most famous one is acetone. Stuff you use in nail polish remover. There it is. That is a common name. The technical name is propanone. Prop meaning 3 carbons. And notice the endings. The ONE ending is ketone. The AL ending indicates aldehyde. ANE, alkane. ENE, alkene. OL, alcohol. Carboxylic acid, ethanoic acid. That indicates carboxylic acid. So here's the slide that I was kind of trying to find. This is kind of what you're responsible for learning in terms of, hey, what kind of compound is this? What functional group is present? What would you call this kind of compound? So let me explain this a little bit more. In organic chemistry, this R thing, there's no R on the periodic table, not by itself. R is a generic carbon chain. That's what it means. Whether it's 1 carbon, 2 carbons, or even, well, yeah, usually carbon. So yeah, replace any of these R's with a carbon chain of any length, and you can make that compound. So notice that aldehydes have to have a hydrogen here. Ketones should have carbons on both sides. The only one that's a little bit funny here is amines. So amines, even though it says RRR, you can have a hydrogen there. It's fine. And it's still an amine. Or you can have a bunch of carbons on either side too. And here we've got the condensed version of this. So if you see COOH, that's acetic acid. Or that's an acid. So acetic acid we often write as CH3, COOH. Because that COOH clues us in, hey, that's an acid. The regular formula would be C2H4O2, which doesn't tell us anything, right? So that's why condensed formulas are preferred over plain old count the atoms formula, okay? Okay, so this is what you should kind of look at for the future. And I know that you haven't had a chance to memorize it, but let's take a look at some examples of what you might see. So top left, what kind of compound is that? Well, got a bunch of carbons, of course. Focus on this part here, a C double bond O, and an O next to that carbon with more carbons on either side. That is an ester to me. If I go back one slide, there it is, an ester. C double bond O with an O and more carbon, more carbon. That is definitely an ester. Here, I don't see any other atoms besides carbon and hydrogen. So you can focus on that triple bond here. That is an alkyne, Y-N-E, alkyne. Here, we've got this O right here that's kind of sticking out. That is an ether, yeah, ether. This one, aldehyde, yeah. C double bond to O, carbon on one side, hydrogen only on the other side. That's an aldehyde. That one, so there's that classic benzene ring. Well, but it's got the benzene ring, so it can do resonance. That's a special kind. That's an aromatic. Aromatic, yeah. Kind of an alkene, but not exactly. So this kind of makes it the aromatic thing, okay? And then this finally is just an alcohol. This is, how would we call this? This would be methyl, 2-methylpropanol, or sec-butanol. There's a lot of different names for it. Anyway, don't worry about it. Organic is, yeah. So the problem with, and it's not the problem, what makes organic such a big branch of chemistry is its carbon. Carbon, you saw, can have 4 bonds. And it can do these gigantic covalent networks, but it can also do these complicated structures of small molecules too. That's why we exist, is because carbon can do all this stuff. Okay. So, now that we have this this framework set in place, because we're going to talk about different functional groups in a little bit, let's get to states of matter and intermolecular forces. So I think everybody knows how solid, liquid, gases work, but let's just kind of remind you. That works good. Come on. my God. Come on.
Just making sure you really want to watch it.
Yep.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature.
So, first, before we get any further, this is a solid. It's below the melting point. But notice that there's already these atoms that are the same atoms as the solid. They're flying around. There is gas present of this that's made of the same substance. And we're going to look into this in detail later, but people don't realize that everything will emit gas a little bit. So we are emitting gases. I guess the best evidence I can give you is if you have ice in the freezer that's been sitting in your ice trays for a month. Well, I don't know if people still have ice trays, but if you've got ice that's really, really old, it's gonna lose its shape. It's gonna get smaller. They shrink, and that's because the solid ice, even kept at below freezing, will vaporize slowly over time. That's why people have frostless freezers. It takes those gases and removes them. If you don't have one of those freezers, you got like the dorm freezer, it gets covered in frost eventually. But yeah, so there's gas present even at the solid form.
Because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase.
And even at the liquid form, there's gas. That should be more obvious to people. How does water evaporate when it's not at the boiling point? It makes gas, even in liquid form.
At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy.
All right. So, just to get a
On
visual.
this graph of time versus temperature,
We can talk about that later. So this visual just hopefully reminds you that, what they look like in solid, what they look like in liquid form and gas form. So when molecules are in solid form, what's keeping them together? For ionic solids, for covalent networks, for metals, I think it's easy to see what's holding them together. It's the bonds, ionic bonds, it's covalent bonds like a diamond, or it's weak metallic bonds in a metal. But what about for a molecular solid like dry ice, CO2? CO2 is a bunch of CO2 molecules that are just kind of near each other, and they stay near each other. Why do they stay near each other? So this is the explanation, intermolecular forces. There's some kind of additional forces besides the main bonding forces we've studied. So that's what we're going to go over. So there it is. There must be some attractive force keeping the particles together at close range. So Coulomb's law is a really basic equation. It's a physics equation. You have two particles that are charged, and based on the distance between them, you can calculate a force of attraction. And while we use this for ionic compounds, and of course we use this for electrons attached to an atom, with this nucleus, we can sort of use it for intermolecular forces as well. So the hint here is intermolecular forces is going to involve charges somehow. Let's get to it. We're going to identify all the different kinds of intermolecular forces. Well, we probably won't get to that today. We're going to, some compounds have more than one kind of intermolecular force in play. And so if that's the case, we'll identify the dominant one. And we'll use those explanations to explain boiling point and other physical properties. So we'll start simple. This is Model 1 in Chem Activity 25. You can see two different pictures. I'll let you guys read it to understand what you're seeing. But it's liquid versus something evaporated. And then Model 2, which we'll go straight into it afterwards, is 3 tables. And notice that one table is all alkanes, The next table is all ketones, and the third table is all alcohols. So this is the reason why we looked up functional groups. We need to understand the difference between them and why we might get different results. So let's try, and I believe it's on page 63, questions 1 through 11. We'll take 10 minutes and we'll talk about it. Oh. That's it. Yeah, 1-propanol is different from isopropanol. Isopropanol, the OH is in the middle of the molecule instead of on the end. Yeah, lots of different names. Have fun when you use it. I will say the naming scheme is very systematic though, so once you learn it, you'll be like, pretty logical, it makes sense. It has to be. This is T's. don't draw proper Lewis structures in organic chemistry. We just draw the atoms with bonds. So whenever you draw COH, there are 2 lone pairs of those oxygens. And so there's 4 groups of electrons that makes a tetrahedral electron geometry. So everything has 109.5-degree angles.
Okay, yeah.
So that's a bent bond.
Oh, yeah.
Yeah, it would be bent, maybe not 90 degrees, but it would be bent. Yeah. So 109 degrees. This is how I would draw it, which is not a big deal, not very different from what you did, but which one is it? Is it butane or which one is it? Propanol. Okay, so let me get a blue color that shows up. I would draw it like this. So the hydrogens are actually like this. So if you wanted to draw it 3-dimensionally, that is a better way to think about how it might look. Sorry. So everything is bent. It's like all zigzaggy. It's 109.5-degree angles. So that angle here is approximately, not exactly, at 109 degrees. It's probably less even, because the more lone pairs you have, the more squished that angle gets. But everything's bent. And that'll affect whether there's a dipole or not. Okay. So they're hydrogens got an arrow pointing to oxygen. Carbon has an arrow pointing to oxygen. But they're not opposing. They're both pointing in one overall direction. Yep. And even if they were pointing directly at each other, they're not equal. Like they're not like equal polarity. So there'd be a little bit. It is really polar. It's not. We'll see how polar it is. You'll see. Yeah.
It's implied that I know what you're saying.
Correct. Yes.
That's a more effective joke against you.
Yeah, so in our 221, we did polarity at the pretty much the end of 221. I'm not sure if the other classes, schools, did too much polarity stuff before this, but if not, come and talk to me. We can give you a quick, like, dirty rundown on how to do it. But okay, let's do some results because it's been 10 minutes. So hopefully you circled the big one. That's the one after evaporation. And this is just a gentle reminder that when water is doing a physical change, evaporating, there are no differences in particles before and after. No bonds are broken. And you can see it right there. There's a water molecule, still the same water molecules. So no bonds broken. And 2 is not my favorite question. I think it's a little confusing. But on average, are intermolecular forces stronger in liquid hydrogen or liquid water or gaseous water? Technically, the answer is that they're stronger in the liquid form. And the reason for that is distance between the molecules. The closer the distance, think of Coulomb's law. The closer the charged particles are, the stronger that attraction is going to be. Now, what I don't like about it is there's no difference between these water molecules and these water molecules. So they still have the same potential to attract other water molecules. It's just the distance is what's in play here. And what's making the distance so great? It's the kinetic energy. We've given these water molecules a lot more energy, so they're going to move faster and be less likely to stay near each other. That's not, like I said, it's not the best explanation, but that's what's going on here. We're gonna refine that idea later. So the next set of questions concerns these graphs, which I'll go back to the other slide. Not these graphs, these tables. So what's the Lewis structure, and then predict which bond will be the shortest and what the COH bond angle will be. So I didn't actually draw the formal, I did draw a Lewis structure, but I drew the Lewis structure with shape. And the bond angle, since this is tetrahedral, 1, 2, 3, 4 groups of electrons is tetrahedral electron geometry, then the bond angles are going to be approximately 109.5 degree angles, tetrahedral. And in terms of the shortest bond, what is the shortest bond? No, so just a single bond between two atoms. Which bond is the shortest? The oxygen-hydrogen. Because, first of all, hydrogen is the smallest atom. And the next smallest atom would be the oxygen, right? Carbon versus oxygen on the periodic table, neutral atoms. Oxygen, you get smaller as you go to the right. All right, so oxygen is a smaller atom than carbon is. And so this, like the CH bond here versus the OH bond. The OH bond is shorter because we have smaller atoms. Okay. So recall that the electronegativities are roughly the same for hydrogen and carbon. Depends on the chart you look at. The one I remember, 2.1 for hydrogen, 2.5 for carbon. They're different, but not that different. Oxygen, though, is about 3.5. That's very different. And so when we look at a carbon-hydrogen bond, in general, think of it as a non-polar bond. So carbon-hydrogen, it's not polar at all. But as soon as you throw the oxygen in there, you get polar bonds. And when you look at this thing, remember polar bonds, you draw a dipole moment for each bond. So there's a polar bond here. And I'm going to draw an arrow towards the more electronegative element. Put a little plus sign on the tail. There's another polar bond here. It's not as polar, but it's still polar. And that goes this way, towards the oxygen, the more electronegative atom. If these were directly opposing each other and the same length, then they would cancel out and be nonpolar. But they're not. They're both pointing overall in this direction. And so this is a polar molecule. When you add up all the polar bonds together, this is a polar molecule. The ketone is the same thing, or not the same thing, but similar. If you have this in here, yeah, all the rest of these things are nonpolar, but this part is pretty polar. There is a dipole moment going in that direction. And that's it. That's the only one. So that's overall, that's the polarity of the molecule right there. So these are polar. The alkane, which has no oxygens in it, is nonpolar. All right. And then for each compound below, indicate how the boiling point changes as the molecular weight. Well, here's the alkanes. As you increase molecular weight, the boiling point, here I should use this. As you increase the molecular weight here, the boiling point increases. As you increase the molecular weight of ketones, the boiling point increases. As you increase the molecular weight of alcohols, the boiling point increases. So they all go up as your molecular weight increases. Now I'm going to kind of warn you against thinking that molecular weight is the cause. It's not the cause. It's just molecular weight correlates with the increase in boiling point right now. Okay? It's a different meaning. So, how do the intermolecular forces between molecules change as molecular weight increases? Well, it goes up. So, as molecular weight increases, we see the boiling points go up, which must mean that the forces keeping the molecules together are getting stronger. That's why it takes more energy. You have to have a higher temperature to get them to break apart. Now, let's find an alkane and a ketone and an alcohol that are roughly the same molecular weight so we can eliminate that variable, right? We're keeping it constant. That's making it a controlled variable. That's the term. And let's compare them. So if I look at butane, which has a molecular weight of 58.1, and acetone, which is exactly the same molecular weight, propanol is a little bit higher, but approximately close to the same. And if you compare these three, minus 0.5, 56.2, 117. So it's pretty clear that the alcohol has the highest boiling point when all the molecular weights are similar. Next is the ketone. There it is, 79.6. Am I looking at the right one? No, I looked at the wrong one. Sorry. I did 58.1, minus 0.5, 56.2, 97.4. There we go. That's the one I was supposed to look at. But yeah, the alcohol is still higher, then the ketone, then the alkane. If I do it again with another set, 2 more sets. So let's try the 72.2 molecular weight. That's similar to 72.1. That's similar to 74.1. It's 36 to 79 to 117. It's the same pattern. Alcohol is higher than the ketone, which is higher than the alkane. Okay. So we found a pattern, and it's pretty consistent. Alcohols have higher boiling points in general. Ketones are next. Alkanes have generally lower boiling points. So what must that mean in terms of their intermolecular forces? Alcohols must have strong intermolecular forces. Ketones have slightly weaker intermolecular forces. And alkanes must have very weak intermolecular forces. So how do we explain that? What is causing them to have strong versus weak IMFs? Well, we noticed that the alcohol and the ketone both have a dipole moment, whereas the the alkane does not. And so it must be something to do with the dipole moment. We'll get to the relative strength in a second. But last question, 11. Is the strength of the intermolecular forces determined by the bond strengths within the individual molecules? So this is, be careful of how it's worded. They're basically saying, does the strength of this carbon-oxygen bond have anything to do with the boiling point? Does the strength of this carbon-oxygen double bond have anything? So this is actually a stronger bond than this bond, right? A carbon-oxygen double bond is stronger than a carbon-oxygen single bond. And yet, this has a higher boiling point. That is a weaker boiling point. Whereas the alkane is the weakest. So it has nothing to do with the bond strengths. So it has nothing to do with the internal bonds of a molecule. It has to do with how it's perceived out from the outside. So something to do with the dipole moment. Okay? Okay. So we covered this as the molecular weight of the compounds increases, the boiling point increases. And in terms of IMF strength, your alkanes are the weakest, your ketones are next, and your alcohols are the highest strength, IMFs. And the presence of a dipole moment in the molecule tends to increase the strength of the intermolecular attractions. So we're starting to understand how IMFs come about. And here is another chart that's interesting. So ignore the red area here for a second and look at this part here. And what you're seeing are compounds made from a nonmetal and enough hydrogens to make it a single molecule. So everything in group 6A needs 2 hydrogens to be happy. And so here's H2S, here's H2 selenium, here's the next one down, H2 tellurium. This is with carbon, so this is with silicon, that's with germanium, that's with tin. So as you go to lower in the periodic table, which is what this is happening, period 2 to 3 to 4 to 5, the boiling points are slowly increasing. And that should make sense, right? Because we just learned that as the molecular weight increases, the boiling points tend to increase. So what about the difference between these lines? What about the difference here? What is going on here? So we have to get to a little bit more to the bottom of this. So let's kind of look at the dipole moment stuff in detail now. And let's explain the terminology we're using. So there's a difference between intra and inter, first of all. When we talk about intramolecular forces, which we're not going to use very often, the word intra means within the molecule. We're talking about the bonds, covalent bonds that are holding two atoms together. That's an intramolecular force. And these are generally really strong. Ionic and covalent bonds are pretty strong. They take lots of energy to break, on the order of 100 to 1,000 kilojoules per mole. And then these intramolecular forces, these are the ones that control chemical properties. You know, does it react? Does it burn? Things like that. So we're going to be focused on intermolecular forces. These are the forces between two different molecules. And these don't influence chemical properties generally. They influence physical properties. They're much weaker. Notice that the energy to break them, to separate two molecules, is a lot weaker than the energy to split a bond, for instance. These are the kinds of intermolecular forces we're going to be studying. So ion dipole, 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 London dispersion, hydrogen bonding. And I'm not a fan of this being in here, ionic bonding. This is one of the intramolecular forces we usually talk about. But technically, what is the smallest particle in an ionic compound? It's the ion, right? So they're held together with forces, at the same forces that intermolecular forces are held together with. So, or molecules are held together with. So even though we think of ionic bonding as one of these kind of bonds, like an ionic bond here, you can kind of include it down when intermolecular forces too. That's a technicality. We don't normally think of ionic bonding as an IMF though, okay? So here's another sense of scale for the energies involved. For ionic and covalent bonding, they're pretty high. This is the energy required to break the bond. Here are two different kinds of intermolecular forces. So there's the standard van der Waals forces, which we're going to cover. And then there's something special called hydrogen bonding, which is a little bit stronger. But these are really weak compared to that, just to give you an idea. So let's start with the basic IMFs that we're going to study. And here is going to be a little bit of frustration. These slides have pictures from different textbooks, and every textbook categorizes them, groups them a little differently. Because I want you to see that, you know, over here we've called something van der Waals forces, and we've separated dipole-dipole and these London things. We'll talk about that, and hydrogen bonding. Over here they put it all together. And then over here we included ion dipole and ionic bonding, and over here we don't have any of that. So every book kind of groups them, lumps them together differently. What's important is you understand what the force is, like what is happening, why is it called something like that, and then just the relative strength, okay? So we're going to focus on these three mainly. London dispersion forces, or London forces, these are the weakest. They may be the weakest, but they're the most important because everything does this. And we're going to get into what it is in a little bit, okay? But every molecule will do London dispersion forces, everything. But some molecules will also do dipole-dipole forces. And that's kind of what was happening over there. When you have a molecule that has a dipole in it, it will interact with another molecule of the same molecule or a different molecule that also has a dipole in it. And those are fairly strong in terms of IMFs. It's in the middle of the road. There's a special case of technically dipole-dipole forces that is called hydrogen bonding. And it's a very limited scenario, but it's really important in biochemistry. and biology. And we'll get to that in a second. So that's the strongest. So we'll go over these three. But before we go over these three, let's start with, and here are the three groups that we just studied. Alkanes will only do London dispersion forces. Ketones will do London dispersion forces and dipole-dipole forces. Alcohols will do London dispersion forces, and it's got a special kind of dipole-dipole force called hydrogen bonding. And that's why it had the highest boiling point. Okay. So just kind of, this is bringing us back to the data that we looked at. This is why the alcohols were higher molecular weight, boiling points in general. Okay. Now, let's look at even stronger than hydrogen bonding. We'll get to that in a second. So here's another intramolecular forces. These are the bonding forces. We have ionic bonding, covalent, metallic. There we go. The energies. Notice that metallic bonding is slightly weaker than the rest of them, but still pretty strong. So here's the first intermolecular force that is probably the strongest. And you only get this when you have a mixture, okay? You can't have this when you have a pure substance. So it has to be a mixture. This is what happens when you dissolve any salt in water, basically. Is you get these ion dipole forces. So what is that? Well, you've got ions present. So like a cation and an anion, like sodium and chloride, something like that. And then you've got a molecule that has no ions in it, but it has a dipole moment. Like water. Water has a dipole moment. Water is polar. And so what we're seeing here is, instead of showing the actual molecule, we're showing a representation of its dipole moment. So any molecule that has a partial positive side and a partial negative side to it has a dipole moment and can interact with ions. So these anions will attract the partial positive sides of the molecules we've got it dissolved in, like water. And the cations will attract the partial negative side. And by the way, this is the lowercase Greek letter delta. That means partial, not a full -1 charge, a fraction. It could be a large fraction. It could be a really tiny fraction. It's not necessary to know, just that it's not a full charge. And we can talk about how this works with Coulomb's law. Coulomb's law, remember, is force is equal to some constant times the charge of one particle and the charge of the second particle over the distance squared between them. And while Q2 might be a full +1 or it might be a full -1 charge, Q1 is going to be a fraction instead. Instead of a full +1 or a -1, it'll be a 0.2 or 0.1 or even smaller, 0.01. And so your forces are going to be a lot smaller because you've got a fraction here. But there's still going to be a force. There's still going to be an attraction. And it is significant enough that that's why water can dissolve things, right? Think of an ionic compound, sodium chloride in solid form. You've got positive cations next to anions in a crystal, and they love each other. They love being each other. The positive attracts negative. So why would they ever separate? Well, water has enough of an attractive force to interact with those ions and dissolve it and spread and pull apart the ions and have it dissolve. It doesn't work on everything. There are some salts that are not soluble in water. If I told you one, magnesium oxide is not soluble in water. Why would it not be soluble in water?
Me.
Well, you don't have to answer. Anybody know?
The charges are bigger.
The charges are bigger. There is a +2 charge and a -2 charge attracting each other. Water is actually not polar enough to attract oxygen or magnesium ion over the attraction they have for each other. And so it's not soluble. So we're getting into now explaining why some things are soluble and some things aren't. So that's why IMFs are important. We have to understand them. Yeah, good.
Yeah, so if you look at that bottom left polar molecule and the top right polar molecule
Uh-huh.
on the right one, they're the same orientation. Does it turn into some sort of lattice where it does double duty and
Oh,
navigations?
oh, I see what you mean. Like this is next to that. I think in a liquid, the motion is random enough where it doesn't. But there's some funny stuff you can make. There's like gel solids you can make. Maybe that is involved. I don't know.
That's
I don't know.
Okay.
I'm not sure. Yeah.
Just following up on that, is this how like salt melts ice or prevents ice from forming?
Okay, that's slightly different. Well, it is and it isn't. So, we're gonna get into that. I think that's 223. But the reason we put salt on ice on the sidewalks, it kind of is a little bit. It will break the connections between water, but it also adding particles will lower the melting point, or lower the freezing point. So they'll have to be at a lower temperature to freeze if there's any ions mixed with the water. So I guess it's twofold. Yeah. All right. So there's a picture of sodium chloride. Happy to be a solid, but if you dissolve it and if you put in some water, their water will break it apart. And that's because even though these chlorides and these sodiums are low energy next to each other, right? They lower the potential energy. That's always what everything wants to be, in the lowest energy state possible. This is just as good, and so it'll dissolve. But MgO, not as good. It will stay as a solid. It won't dissolve. Okay. So this picture here is, I'm not going to make you guys vote for this one, but here we've got a picture of two different sets of molecules. One of them is a solid. Hopefully it's kind of clear that that one is a solid because it's kind of crystalline. Everything's in well-ordered arrangements. Everything is kind of, doesn't look like it's moving. This is not well-ordered. I mean, yes, this could be an amorphous solid, but this is what you see in a liquid. But I guess the big takeaway here is in both the solid and the liquid, intermolecular forces are keeping them somewhat organized. So in a solid, it's very rigid. It has to be like this to be crystalline. But in a liquid, they're still kind of oriented in a way where positive is next to negative. Okay? All right, so we looked at ion dipole. And again, that only happens when you have a mixture. So that's a special case. But what about a pure substance, like just having a ketone by itself, or just having an alcohol by itself? So dipole-dipole forces. These are the electrostatic forces that act between two polar molecules. So now you've got a weak charge and a weak charge together. That's weaker than ion dipole, of course. The orientation will maximize attraction. So if you've got them oriented the wrong way, they won't attract. So this is where shapes of molecules and stuff is going to play a bigger role. The stronger the dipole moment, the stronger the IMFs are going to be. So how do we judge a dipole moment? We'll get to that. So here are some examples of molecules that have dipoles in them. There's CO, carbon monoxide. We've got chloromethane. And then, of course, we've got the inorganic here, sulfur dioxide, all of them polar. Sulfur dioxide is bent, so that's why it's polar. And just FYI, if you forgot how to tell if something is polar or not, if it has the same molecular geometry as the electron geometry, so if something is tetrahedral, and the outer atoms are all the same, it's nonpolar. But if anything is different, then it's going to be polar. So that's tetrahedral electron geometry, tetrahedral molecular geometry, but we've got the outer atoms are not the same. We've got one chloride in there, so that's polar. If they were all the same, methane, HCH4, then it'd be nonpolar. So these forces explain lots of things. So we talked about solids dissolving in the water. What about ammonia? So you guys probably hopefully have heard of household ammonia, which is a cleaner that stinks. It's very, very effective, but it's kind of fallen out of use. Ammonia actually is a gas. It's in a pure form, it's a gas. So the household ammonia that we buy at the store is ammonia dissolved in water. And it dissolves really, really well in water. Why? Well, there's ammonia. It's got a nice dipole moment going this way. There's a positive side, negative side. And it's attracted to the dipole moment that water has. These mix super well together. You can get a lot of ammonia dissolved in water. And it stinks because gases are always coming out of it. Anyway. So here is a kind of a comparison of different kinds of functional groups and their dipole moments. So there is a way to measure dipole moment. We did this in lab in 221, the last lab. We did a computer simulation. We built a model in a computer and then had it calculate a dipole moment. The units of dipole moment are the dBi. Don't worry about it too much, but that's what this is. So the larger the dBi value, the stronger the dipole moment is. These are all almost the same molecular weight, so we're trying to keep it the same. And you can see that as we change the functional group, the dipole moment increases and the boiling point increases. And this may not seem like a big change, but that's because we're starting from 0 and we're showing like a huge scale. So notice we go from 225 Kelvin all the way to 350 Kelvin. So that's a big change. So something like this, acetonitrile, is a huge dipole moment, and it happens to be very high boiling point. Just in case you want to know what that looks like, acetonitrile is this. So that C triple bond N makes a huge, it's very, very polar. Let's put it that way. Here's acetaldehyde, aldehyde group. Ethers are very, very minimally polar. And here's an alkane, which is nonpolar. Or pretty nonpolar. It's not exactly 0, but it's pretty low. This is a weird compound. We're not going to worry about this. But there's a carbon-carbon bond, and there's an oxygen that's connected to both carbons, like making a 3-ring connection. It's a very unusual compound. Let's put it that way. But anyway, goes up as you increase the dipole moment. So that's pretty not surprising. So this is going back to that graph we saw. And we could explain how, as you go to higher molecular weight atoms, the boiling point increases. But what about the difference between the different groups on the periodic table? Like, why were some higher than others? And so if we compare, for instance, group 4 hydrides with group 5 hydrides with group 4 hydrides, what do you think? Let me turn this on. I can't find the clicker. Do you think the group 5 hydrides have a higher boiling point or lower or the same as group 4? Oh, there it is. There's a lot of different ways to think about this. If you want to guess, it's okay. All right, we'll stop it there. That's awesome. That's good. No, it's fine. But, because you guys don't exactly know yet. So let me try to show you a different way to think about it. So what if I drew the NH3 and the CH3? So NH3 looks like this. And CH3 looks like this. Or CH4, excuse me. What's the big difference between these two? There's a lone pair. The shape, this is trigonal pyramidal. This is tetrahedral molecular geometry. Which one is polar? This is definitely polar. Based on the shape, this is nonpolar. So in terms of boiling points, which should have the higher boiling point?
Top one.
The top one. The more polar one should have the higher boiling point. That's one way to do it. So, yeah, this one's higher. Another way is to look at difference in electronegativities. So, the larger the difference in the electronegativity between the bonds, the larger the dipole moments are going to be. So, carbon versus hydrogen, silicon versus hydrogen, germanium, all the group 4, they're kind of close to hydrogen. The group 5 are a little bit further away in their electronegativity from hydrogen, so they're going to be slightly higher boiling points. They're going to make a more polar bond. I like this one better, but because this is really clear. But again, look at the difference in electronegativity. That'll tell you how polar the bonds are, and then you add up the bonds to see if you get a polar molecule. So it's all back to electronegativity. This is going to shadow you for the rest of your chemistry career if you take chemistry some more, okay? It's very big in organic chemistry too. Okay, so there's the chart that kind of refers to what we're talking about. The group 4 ones are generally lower than the group 5 hydrides. But we haven't quite gotten to what's going on here. If this was following a trend, it should be down here, same with CH4. So something's going on with nitrogen. And I don't want to talk about that yet. So let's not do this yet. I want to talk about the next kind of intermolecular forces. So how do nonpolar molecules make solids or liquids if they have no dipole moments? Where does the IMF attraction come from? So you have to remember, so this is what, if you did the lab last term where we calculated the electrostatic potential around the molecule, we kind of figured out, well, is there a region of the molecule that has more electron density than the other side, and so it got more reddish and the other side got bluish. These are nonpolar, so it's just green all over. It's pretty evenly distributed electrons. Well, that distribution of electrons is not static. So the electrons are moving, right? They're always moving. And that's the idea. So London dispersion forces, or London forces, or dispersion forces by itself, they all mean the same thing, relies on the fact that these clouds of electrons are distortable. They are squishy. You can distort that cloud of electrons. They're moving all the time. And so, this probability distribution is only a probability. Like, what's the probability of finding the electron here? It's a mathematical answer. Oh, the chance of finding it here is whatever percent. But if you think about, well, physically what's happening, these electrons could be temporarily more on one side of the molecule than another. And what will happen is you'll get something called an instantaneous dipole moment. It's not a permanent dipole where the electrons are almost always on this side of the molecule and never on that side. So it's partial positive on this side, partial negative on this side, partial positive on this side. It's only temporary. So you could have a very temporary scenario where the electrons are more on one side than the other. And for a brief moment in time, you'll have a slightly partial negative charge on one side and a slightly partial positive charge on the other. And this squishiness of an atom, this ability for the atom's electron cloud to be distorted is actually a property. It's called polarizability. And it's in the word. It's how can you make this cloud polar? Is it polarizable? And so the more polarizable an atom or a molecule is, the stronger the dispersion forces are going to be. Now, just to give you an idea of what we're looking at here, this is just 2 helium atoms. Helium is neutral, spherical, doesn't want to bond. It's fine by itself. And let's just say that at a snapshot in time, we've got 2 heliums near each other. In this helium atom, the electrons are temporarily on this side of the molecule, of the atom. What will happen? The negative charge on this side of the molecule might repel the electrons in this atom and might make them move to this side of the molecule temporarily. And you'll get kind of this scenario where you'll get a partial negative here and a partial positive here, partial negative, partial positive on opposite sides. And it'll exist for a fraction of a second. And that fraction of a second is enough to make a slight attraction between them. But then they'll go flying and reset. Imagine that happens with 6.022 times 10 to the 23 atoms. It's as rare as it is, it's going to happen a lot. And that is enough to create small, minute attractions that allow nonpolar compounds to become liquids and to become solids. So even things that have no permanent dipole moment can be attracted to other things through these really weak dispersion forces. So what's required for dispersion forces to work is just electrons. Yeah, question?
Just wondering, wouldn't it be just as likely for these to instantaneously repel each other?
So that would require both of them to be coincidentally having electrons on the same side, which can happen. But if one of them is fairly neutral and the other one temporarily has a partial negative, it will influence the other one to do the same thing. Much the same way with the superconductor thing with the opposing magnetic fields.
There's more ways for it to attract than repel.
I think, yeah, there's more ways for it to attract, yes. I believe. Now, again, every molecule has electrons, so every molecule atom will do dispersion forces. But the more polarizable your electrons, the stronger your dispersion forces are going to be. So what kind of atoms might be more polarizable? So if I compare fluorine versus iodine, what's the difference between fluorine and iodine? Big difference, right? The valence electrons in iodine are where? Shell 5. They're far away from the nucleus. Are they loose? Are they influenced by the nucleus very much? No. Those electrons are very polarizable. Whereas a fluorine valence electron, super close to the nucleus, harder to influence. They're less polarizable. So think about this. Why is I2, the molecule I2, that's a solid at room temperature, whereas F2 is a gas at room temperature. And it's all because of the fact that iodine is way more polarizable. It has much stronger dispersion forces. So even though it is considered to be the weakest of the IMFs, dispersion forces are the weakest, they can be very strong. They can make things solid at room temperature. And it all has to do with number of electrons and how polarizable they are. So here is a picture showing kind of what's happening. We've got two neutral molecules. They're nonpolar. And when one approaches the other, and this is, it can happen lots of different ways. In this particular way, this causes the electrons in this molecule to move over to this side temporarily, causing the electrons here to be attracted to the positive side of this molecule. You get a temporary dipole, which will reset after a fraction of a second. And when I mean a fraction of a second, I mean like a really small amount of time. But, if you multiply that over not even trillions, more than that, 10 to the 23 atoms, that happens often. Let's put it that way. And so you get attractions. So Cl2, these are nonpolar, and then suddenly they make instantaneous dipole moments. And, they fluctuate. It goes away, comes back, goes away, comes back. So just to give you an idea of how weak they are. And so for helium is an extreme case. Helium is probably the least polarizable atom there is. The forces that could hold two heliums together are about 0.1 joules per mole, compared to 100 to 1,000 kilojoules per mole. So that's an order of magnitude, I think 5 times difference. Is that what? No, more than that. 10 million times smaller. So, yeah, 7 or 8 times difference. Not order of magnitude 7 orders of magnitude different. That's what I wanted to say. My grammar sucks today. Sorry. So it's a really weak force, but it can be a lot stronger. Helium's probably the weakest one. So now, if we come back to this idea of molar mass, why was molar mass influencing boiling point? Well, what happens when you have higher molar masses, generally? So how do you get more molar mass? You either pick an element that has a heavier molar mass, which could be more polarizable, or you have more atoms, more carbons. And what do more carbons give you? More valence electrons. What happens when you have more electrons? More ability to have instantaneous dipole moments. So it's not the molar mass that was causing the molecular weight. That was a correlation. It's just a correlation. It's the fact that the more molar mass you have, the more likely you have more electrons, or you have a heavier element that has more polarizable electrons. And that's what's causing the increase in boiling point. So I want to stop there because that's kind of enough information. So we've studied two of the main IMFs, dipole-dipole forces, and we've started to get into London dispersion forces. There's a lot more to it. We have yet to talk about hydrogen bonding, but we'll get to that too. Okay? So Thursday.
We do a quiz on Thursday.
Oh, yeah. I would say no, unless you really want one.
I mean, I prefer not.
No, let's do not, because we don't have anything scheduled, or like nothing. There's no new material yet that we haven't been tested on.